Hi, in this video we are going to discuss hydrogen bonding. This is the beauty of chemistry that one deep concept can solve different questions, and if you understand the concept once, you will never need to memorize it again. Today we will uncover those master keys. We can't say that hydrogen bonding is only intermolecular force or intramolecular force, but we can say that hydrogen bonding is electrostatic force between hydrogen and highly electronegative atoms which have lone pair electrons, such as fluorine, nitrogen, and oxygen. Now, the question is this: what is electrostatic force? As the word electrostatic indicates, this is a force between two objects or charged particles, which are at rest. This is a type of non-contact force. This is because the force acts through space and charges don't have to touch each other. For example, in hydrogen fluoride molecules, the force which develops between hydrogen and fluorine atoms is electrostatic force or hydrogen bonding. Electrostatic force can be attractive and as well as repulsive. This is a type of attractive force. We can also say that this is intermolecular force. But hydrogen bonding or electrostatic forces can be intramolecular forces as well. So we can say that there are two types of hydrogen bonding. These two types of hydrogen bonding affect physical properties, structure and reactivity in very interesting way. But before to discuss the effects of hydrogen bonding on physical properties, structure and reactivity, we discuss its two different types. Intermolecular hydrogen bonding. This is a type of hydrogen bonding which develops among same or different types of molecules. For example, as we have discussed that the forces which develops between hydrogen and fluorine among hydrogen fluoride molecule is a type of intermolecular forces. And the forces which develops among water molecules are also intermolecular hydrogen bonding or intermolecular forces. And the second type of hydrogen bonding is intramolecular hydrogen bonding. This is a type of hydrogen bonding which develops within a molecule. For example, hydrogen bonding which develops between hydrogen and oxygen in salicylaldehyde. This is a type of intramolecular hydrogen bonding. One of the isomer of this compound, para-hydroxybenzaldehyde, has intermolecular hydrogen bonding. These two isomers having the different types of hydrogen bonding shows different physical and chemical properties, such as the first isomer is less acidic, less reactive, and less soluble in water. And this one is more reactive, more soluble in water, and more acidic. Let us now we explore how hydrogen bonding affect physical properties like melting and boiling point. Those molecules which show intermolecular hydrogen bonding, their boiling point is higher as compared to those molecules which don't show hydrogen bonding and have intramolecular hydrogen bonding. For example, water shows intermolecular hydrogen bonding have higher boiling point as compared to ether and petrol which don't show hydrogen bonding. This is because water molecules hold each other through hydrogen bonding and cannot evaporate easily. While, on the other hand, the molecules of the ether and petrol do not hold each other and can evaporate easily. And in periods when we move from left to right in the periodic table, electronegativity of atoms increase. This is because effective nuclear charge increase and size reduce. And when we discuss the hydrides of these atoms, such as methane, ammonia, water, and hydrofluoric acid, the hydrogen bonding tendency or hydrogen bonding force is also increased from left to right. This is because electronegativity increase. So we can say that as we move from left to right, molecules hold each other strongly. So their boiling point increase. But hydrofluoric acid have the stronger hydrogen bonding as compared to water, but still this have the lower boiling point as compared to water. Though the water molecules have the weaker intermolecular forces or hydrogen bonding as compared to hydrofluoric acid, but still show the higher boiling point as compared to hydrofluoric acid. This is because one molecule of the water is being held by the four other molecules of the water. Or water molecule can show 4 hydrogen bonds per molecule. And hydrofluoric acid shows 1 hydrogen bond per molecule. This is the reason hydrofluoric acid shows boiling point 19.9 centigrade and water shows 100 centigrade. And when we move from top to bottom in the groups, electronegativity decrease. This is because shells increase and size reduce. For example, when we discuss oxygen, sulfur and selenium which belong to the same group, here tendency of forming hydrogen bond decrease because the electronegativity decrease. When we discuss the hydride of this atom, the hydride of the first atom is the liquid because it shows hydrogen bonding. And the hydride of the second two atoms are the gases because they don't show hydrogen bonding. But when we discuss the group 7 in the periodic table, although the sizes increase from top to bottom, electronegativity decrease and tendency of forming hydrogen bonding is also decreased, but still the boiling point increase from top to bottom. Such as hydrogen chloride have the lower boiling point as compared to hydrogen bromide and hydrogen bromide have the lower boiling point as compared to hydrogen iodide. This is because other forces such as London forces or polarizability increase from top to bottom, which overcome hydrogen bonding and boiling points increase from top to bottom. But hydrogen fluoride is out of this trend, have the highest boiling point. This is because of strongest hydrogen bonding. And when we discuss the effect of hydrogen bonding on solubilities, again those molecules which show intermolecular hydrogen bonding are soluble. For example, alcohols are soluble in water. This is because alcohol form hydrogen bonding with water. And ethers are not soluble in water because they don't form hydrogen bonding with water. And in case of those molecules which show intramolecular hydrogen bonding, their interaction with solvent is restricted so they are less or not soluble. Ice float on water. This is also because of hydrogen bonding. Ice have the empty spaces or low density. This is because of hydrogen bonding. Although the water in liquid form also have the hydrogen bonds, but ice have the stronger hydrogen bond as compared to water in liquid form. It is because water molecules in liquid form keep moving, so their shape and hydrogen bond positions also change. While on the other hand, molecules of the water in ice not move as much as in liquid form, as the molecules of the ice are fixed and hold each other strongly, which develops empty spaces and the density decrease. Hydrogen bonding also affects the structure and reactivity. For example, hydrogen fluoride is less reactive or less acidic as compared to other halogen acids. There are two reasons behind this. The first one is the bond between hydrogen and fluorine is much stronger because of high electronegativity difference. And the second reason is the hydrogen bonding. Hydrogen bonding traps the hydrogen atom between two highest electronegative atoms. So hydrogen cannot remove easily. This makes hydrogen fluoride less acidic or less reactive. And those molecules which form hydrogen bonding after ionization are more reactive. For example, salicylic acid. This is not stable. This is reactive and more acidic. And after losing proton, the anionic species is stabilized by internal hydrogen bonding or intramolecular hydrogen bonding. And we can say that any acid which after losing its proton is stabilized by hydrogen bonding is more acidic. And one of the isomer of salicylic acid, para-hydroxybenzoic acid. After losing its proton, this is not stabilized by internal hydrogen bonding. So this is less reactive and less acidic. So we can say that hydrogen bonding also affects reactivity and acidity. Let us now we discuss the applications of hydrogen bonding. Hydrogen bonding perform cleansing action with detergent. Detergents has two parts. One is the tail or alkyl group which is non-polar. And the other is the head which is polar part. Non-polar part of the detergent develops attractive forces with oily spot on clothes. While on the other hand, the polar head having the negatively charged oxygen develops hydrogen bond with water. And when you flood the water, the oily spot moves out with the detergent and water molecules. Hydrogen bonding also play a role to maintain the structure of deoxyribonucleic acid. Deoxyribonucleic acid has two strand or spiral chains which are held by hydrogen bonding. Actually, these two strands have the nitrogenous bases, which are cytosine, guanine, adenine, and thymine. Cytosine and guanine form triple hydrogen bond. Adenine and thymine form double hydrogen bonds. These hydrogen bonds hold together the spiral chains of deoxyribonucleic acid. Hydrogen bonding exists in proteins. This is also an important part of living organism. Proteins are the polymer of amino acid or long chains of the amino acids. These long chains of amino acid or proteins are spiral, and these spiral shapes of proteins are held by hydrogen bonding. Actually, the amino acid or protein have the carbonyl or amino groups, which form the hydrogen bonding and maintain the structure of proteins. And we use paint and textile materials. Hydrogen bonding is also exists there. Paints have adhesive property. This property is developed due to hydrogen bonding. And we use cotton, silk, and synthetic fiber for clothing. Hydrogen bonding is also exists there and responsible for the strength of these textile materials. Thanks for watching, and please comment if you have any question.